Assalamu alaikum and hello. We are Group 1 and this video is for our MAT097 course. Task 1 explores Luxembourg's population growth using exponential modeling. Task 2 applies a trapezium rule to estimate a definite integral. Let's begin. Let's begin with a question. Can mathematics predict how a nation grows? In this video, we explore Luxembourg's population over 20 years, from 2005 to 2025, and how we can represent this growth using mathematical models. Our purpose is to demonstrate how actual population data can be used to construct and compare different models of growth, particularly through the lens of Malthusian model. By blending real-world statistics with mathematical theory, we aim to gain insights into long-term population trends. Our work is rooted in the Malthusian model, proposed by Thomas Robert Malthus in the late 18th century. Malthus observed that populations tend to grow exponentially, while resources such as food and land grow only arithmetically. This imbalance, he argued, would eventually lead to shortages. Although this model doesn't account for factors like immigration or economic development, it provides a useful starting point to understand basic exponential population trends. To test this model, we collected actual population data for Luxembourg from official sources covering the years 2005 to 2025. These values were compiled in Microsoft Excel, where each year's population was listed and plotted. This dataset served as a basis for both our modeling and our visual comparison. Using the Malthusian assumption of exponential growth, we formulated a first-order differential equation. We then applied initial conditions from our dataset to solve it and obtain a particular solution. This equation models population as a continuous exponential function, theoretically capturing the same trend seen in the real data. Next, we created a comparison table listing both the actual population values and predicted values from our exponential model. This allowed us to assess how closely the models fit the real population trend. As expected, the model fits reasonably well, although some deviations are present, likely due to real-life variables not captured in our equation. Finally, we visualize our findings. The green dot represents the actual population from 2005 to 2025. The blue curve shows the particular exponential solution. The black line represents a linear regression constructed from the same real data. The side-by-side comparison highlights that while both models approximate the trend, the exponential curve more accurately reflects the accelerating growth of Luxembourg's population. However, real-world growth is influenced by policies, migration and economics factors beyond the scope of pure mathematics. We constructed a particular exponential solution, compared it with actual data, and contrasted it with the linear regression. This process not only revealed the power of mathematical modeling, but also its limitations when applied to complex human systems.
Next, I will be presenting the data analysis for our project of Luxembourg population growth using our particular solution. One value from the past and one value from the future was calculated. For the past, we choose t equals to -25 represents the year 1985. Then we substitute -25 into the particular solution and we get 310,827 people. For the future, we choose t equals to 30, represents the year 2040, and we get 753,505 people. The value calculated for 1985 is 310,827, while the actual value is 366,661. So we calculate the percentage error and we get 15.23%. The values calculated from the particular solution are not accurate with the actual value. In 1985, the percentage error between the calculated and the actual value was 15.23%, with the calculated value being less than the actual value.
From the particular solution, there is difference between the actual value and the calculated value. The difference between the actual value and the calculated value due to the fact that the particular solution often assume constant growth rate, while in the reality, population growth can fluctuate over time because of some factors. For example, changes in birth and death rate. In the past, the population growth in Luxembourg has been increasing due to several factors, including economic growth, immigration, and changes in birth and death rate. Additionally, Luxembourg has strong economy, especially in the financial and service sectors, which has attracted many foreign workers, leading to significant immigration. The economic development will really impact the population in the future, as the country continues to offer high-paying jobs and strong standard of living. Now we go to the conclusion. In conclusion, we comprehend completely the application of first-order differential equation from MAT097 in task 1. By using the particular solution derived from the differential equation, we were able to make prediction about future and past population value. We got the value for future prediction in 2040 is 763,505, while for past prediction, we got 310,827. The percentage error that we got is 15.23%, which may be attributed to some factors such as migration, economic events, and pandemic. This project helped us enhance our understanding of mathematical modeling and demonstrate how mathematical method can be used to predict real-life phenomena.
Thank you everyone. Now we are going to move on to task 2. In this part of our assignment, we are required to find the area under a curved graph using a trapezoidal rule. Using this rule, we can find the approximation of area under a curved graph by dividing the curved graph into multiple different trapezoids. This rule utilizes the formula of the area of a trapezoid, which is sum of two different sides times the height and then divided by 2.
Start setting up Excel by inserting xs, fx, coefficient time fx, a, b, and n in the first row in each column. After that, go to the coordinate of f4 and type in delta x. For the first sheet, we will focus on n equals to 6. So, go to the coordinate of h2 and type in 6. Since it's a trapezoidal rule, we'll have to find the h. Therefore, go to the coordinate of f5 and type in as in the picture. Second row, type in the value in A2 and plus it with the number of our h, which is located under delta x with the coordinate of f5. Now, we can drag it down until it reaches the value of b, which is 7. On the next column, we need to substitute the number from the first column into the given equation. But to make it possible, click fx on upper right corner and search for power function. After that, type in as shown in the picture. Now, all you need to do is just drag the box until it reaches the same level as number 7, which is located on the 8th row. Since it's trapezoidal rule, we need to follow the formula's coefficient, which we can observe for a and b should be 1, and the rest should be 2. Now, we'll move on to the coefficient times by the fx. So to make things easier, type in as shown in the picture on D2 box. As usual, drag the box until it reaches same level as b value, which is 7. And click auto sum on the upper right of the sheet to calculate the sum of the coefficient times the fx. Since we're using Excel, all we need to do is write in as shown in the picture. Now press enter and our calculation for trapezoidal rule for n equals to 6 is completed. Moving on to n equals to 10. Start by copying the whole sheet and paste it on the second sheet and change the n value into 10 on the coordinate of h2. Now you can drag the box from xs column until it shows the value of b, which is 7, and do the same thing for fx coefficient and coefficient time fx column by dragging it until it reaches the same level as 7. Click auto sum for column coefficient time fx. On the coordinate of E13, type in as shown in the picture, and now you completed the calculation for n equals to 10.
Thank you, Amy. Now that we are done with the calculation part, we are going to move on to the graph building part. In our assignment, we are required to build two graphs. Both of these graphs contains the limit from 3 to 10. Our first graph contains 6 coordinates and our second graph contains 10 coordinates.
That wraps up our presentation. We've modeled population growth and approximated an integral using numerical methods. This project has given us valuable insights into both the theoretical and applied sides of mathematics. Thank you for watching our presentation. We hope you found it both insightful and informative. Wassalamu alaikum and goodbye.